Now, what's very intriguing is it appears that bar is orientated such that we from the sun can look down the bar to the galactic center. One of the mysteries about the bar is what are the stars doing inside that bar and where did that bar come from? And in fact, one of the greatest mysteries of the bar is whether it's short-lived or long-lived. So we don't actually know the age of the bar.
People argue about this for all galaxies,
Yeah,
whether these are
absolutely.
sudden features that appear and disappear or whether they hang around for ages.
So we'll be able to measure our bar, you know, the nearest one to us, in exquisite detail because, again, because of apogee looks in the infrared, we'll be able to look at stars all the way down the bar. We can see whether the stars are moving along the bar, out of the bar. We can measure their chemical composition of the stars in the bar.
See whether they all form together.
See whether they all form together, see if there's any funny elements in those stars. So apogee, for the first time, really will give us a detailed look of this bar structure in our galaxy.
Well, Sloan has made great contribution to cosmology, and is still doing so, of course, among all other programs.
Yes, Patrick. So originally Sloan started as a galaxy redshift survey, and we were studying, a few years ago, we were studying galaxies quite locally and studying them across the whole sky. But the advances now that they've made in the hardware to the Sloan Digital Sky Survey allow us to make a quantum leap jump outward, so further away from us but closer to the Big Bang, and now study the distribution of galaxies further away from us and add another slice to the cake, if you want to think of it, about the distribution of galaxies between us and the Big Bang.
Well, I'm glad you mentioned that. This project's called BOSS, and when I was last in California, I had a chance to talk to Professor Martin White, who's one of the people working on this, and I asked him what Sloan would do for cosmology. The measurements made by BOSS will help solve astronomy's greatest problem. 3/4 of the energy in our modern universe is in the form of a mysterious accelerating force, which we call dark energy. But what exactly is it?
Well, dark energy is kind of a catchphrase for we don't know what it is, and so we came up with a name for it. And so we observe this phenomena that the expansion rate of the universe appears to be accelerating, which is completely unexpected. And so one way in which that could happen is that we've added some component to the energy density in the universe, which could be just the energy density of empty space, or it could be something even more exotic. And that extra energy in the universe is causing the expansion rate of the universe to accelerate.
So it's powering a new force.
So it's powering a new force, that's right.
How can we measure how fast the universe was expanding in the past?
This method is a very simple one that in principle goes all the way back to the Greeks, but it does rely on two more insights that Einstein had. The first we've already talked about, that the universe is expanding, and as the universe is expanding, that stretches the lengths in the universe, including the wavelength of light. And so if I can measure the spectrum of an object, and I can find in it some emission line or some feature,
something you know the wavelength
something whose
of.
wavelength I know here today on Earth, then I can compare what I see in that spectrum to what I know is on the Earth, and the ratio of those two numbers tells me how big the universe was when that light was emitted. The other thing that Einstein taught us was that the speed of light is finite. And so if I look at an object a long, long way away, I'm looking at it as it was a long, long time ago. And so if I can measure the distance to objects and their redshift, then I can map out how big the universe was as a function of time. And so the question is, how do I measure distances? And there's been several ways that people have tried to do that over the last few hundred years. And one of the most reliable is this idea of really just using trigonometry. If I have some length that I think I know, some standardized ruler, then I can hold that a certain distance away from me and ask what kind of angle does that ruler subtend. And as I get that ruler further and further away, it appears to obtend a smaller and smaller angle. So you want something that's large enough that it can be seen at cosmological distances, that is very, very well calibrated. And of course, it has to be constant not only over unimaginable distances, but over half the age of the universe, so over billions of years.
So what do people use?
What people do is they bootstrap the fact that we really think that the laws of physics haven't changed in those 10 billion years. And so we try and find things that we can calculate just using basic physical principles.
Just using gravity, essentially.
Using gravity and very, very simple properties of sound waves traveling through fluids. And so the idea that we're trying to exploit is known as baryon acoustic oscillations. And to understand sort of where they come from, you have to sort of run the clock back a little bit and imagine running the expansion of the universe back.
The hot, dense environment of the early universe was disturbed by sound waves rolling through the matter that was to become the galaxies that we see today. The signature of these sound waves is still seen in the distribution of the galaxies that Sloan can observe, giving Martin and his colleagues the ruler that they want. While previous experiments, including the original Sloan survey, could see this signature, BOSS will allow astronomers to reach further back, towards the early universe.
And the idea there is to basically more or less take over the Sloan telescope for 6 years and just try and get this enormous volume of space that we need to map out the baryon oscillation signal by measuring the three-dimensional positions of galaxies and then trying to find these echoes of these 500 million light-year shells throughout a volume that is almost 7 times larger than we've been able to do in the past.
How do you get those positions?
So we've got a spectrograph mounted on the back end of the telescope, which we've essentially pretty extensively refurbished. And so, the march of technology means that we have better cameras, better spectrographs, better fibers, better optics, and we're able to design a system now that has much, much better throughput, much, much better efficiency. So we're able to get many more galaxies at a time, and we're able to go much, much fainter, rather than in the old Sloan survey where we really only mapped these very luminous distant galaxies 1/6 of the time. We're now going to do that all of the time.
So I know this is a nightmare of a question, but when should we expect results? Do we have to wait the full 6 years before we hear anything?
It'll be incremental, but there'll be a lag while we really build up, the first useful piece of volume. And so I don't expect that we'll have results on the baryon acoustic oscillations for the next couple of years. And then after that, there should be regular updates that come out as we start filling in the entire survey.
Finding this critical ruler in the galaxies that we see today was Sloan's original purpose. But with BOSS, we should get our most accurate measurement of the distribution of galaxies over cosmic time and be one step closer to understanding our universe's history.
So, Bob, how long will Sloan continue to operate?
That's a very good question, Patrick, and I'm a little worried about answering it since I joined the Sloan originally in 1993 and I thought it was only going to be a 3-year job. It's now 2009 and the Sloan will carry on. We've got funding until 2014, so it'll definitely carry on until then. Maybe there'll be a Sloan 4. It's still very unique hardware in what it can do. And maybe it will keep me going until I retire. So you'll just have to keep asking me back and I'll answer that question in stages.
Well, thank you very much, sir. Thank you very much, Bob. Thank you, Chris. So this is our last programme of 2009. So I hope it's not too early to wish you all a very happy Christmas and New Year. And lastly, don't forget the tiny partial lunar eclipse on New Year's Eve. So until 2010, goodbye.